All right, we're going to take a quick look at how capacitors in a circuit behave. What you're seeing here is a simple circuit that has a battery or power source here. There's a switch here, a resistor, and then a capacitor. And so what we're going to look at today is when you close this switch, say you start your stopwatch right when you close the switch, what we're going to try to do is get the time dependence of the charge building up on the capacitor, and then we're also going to try to get the time dependence of the current running in the circuit. Now, if you remember, we have a couple simple rules for how these capacitors behave. In the very short term, when the plates are empty and you've just closed the switch, the charge is going to really want to rush over to pile onto the plates. And so in the short term, the capacitor is just acting like a wire. And so you can pretend in the short term it's connected and current's just going to be raging around this thing. So you know the current's going to start very high while the charge is low, right? So just using that, you can get at least sort of what the shapes of the charge as a function of time and the current as a function of time would look like. Again, when you start the circuit, the capacitor begins uncharged. There's kind of this mad dash to populate the plates in the early going. But then later on, as charge begins to populate on these plates, it starts looking, less and less awesome for the next charge to come over there. So they're a little bit, as time goes by, the charges are a little bit less enthusiastic about heading over there, but maybe still enjoy it more than being here. They'd still rather be on the plates until they're full. And so if you wait a while, then it all stops and they're full. The plates are full. Likewise with the current in the short going, since this thing is like a wire, in the early going, you can just pretend this is connected here, and it's just a circuit like with one resistor, where your current would basically what you'd get would be what you would get from Ohm's law, just voltage over the resistance. So it starts there, but then as this capacitor starts to populate, the charge is less and less excited to flow over to it, and so you see this tapering off or this exponential decay. So ultimately, what we're going to do today is actually derive these two exponential dependences, right? So the way this works is, again, we've got this same circuit, and our goal is to get the charge as a function of time, the current as a function of time. Well, the way you start this off is by using a Kirchhoff loop. So what happens is the sum of the voltage drop or change on each element must add to zero as you go all the way around. So what we're going to do is start here, go over the battery, the resistor, and the capacitor, and then be back to where we started. So those changes have to add to zero. And so what you do when you do that, the first term is just jumping over the battery. So you just get the battery voltage. We climb the battery voltage. We drop resistance over the capacitor or resistor. And then we get to the capacitor, and we're going to drop again because this will be the positively charged plate, and this will be negative. So we'll be going from positive to negative. So that'll be another drop, and then we'll be back to zero. So climb the battery voltage, drop on the resistor, drop on the capacitor, you'll be back to zero. And so writing those terms out, you have the battery voltage. By Ohm's law, your voltage drop on the resistor is IR, and then by the definition of capacitance, which we defined as C is Q over V, and so V is going to be Q over C, and so this term just comes from the definition of capacitance. So what this does is just lists the voltage changes as you go around the circuit. Well, so what we can do before getting into the nitty-gritty with this is let's just use the what we already know about the short term and the long term. Well, so in the very short term, we know that there's no charge on the capacitor. So this third term should go to zero. The Q is zero. And so what you have is battery voltage minus IR equals zero. And so what you can do is just solve straight away for the current in the short term. So, so the current just starts off at epsilon over R. It's the value you'd get from Ohm's law if this capacitor weren't even there and we're just a wire. And so you can see this this relationship here giving you the right behavior for the current. Likewise, if you look in the long term, the capacitor is going to be filled, and so the current, as you know already, will go to zero. But if the current goes to zero, then you can see that if this second term is zero, then this term and this term must be equal to each other. And so what you end up seeing is then that epsilon is Q over C. So Q is epsilon C. And so you can see that the charge is just going to build up, and this is going to be the value of the charge that you get in the long term. So by using Kirchhoff loops, you can kind of reproduce that same behavior that we sort of already knew just from knowing that the capacitor was like a wire in the short term and like a break in the circuit in the long term. But now let's actually solve for these two dependencies. So again, if you run Kirchhoff loop on this circuit, you go up by the battery voltage epsilon minus IR minus Q over C, and you're back to 0. What we have here is actually a differential equation, because this is well, I shouldn't say that yet. We don't have a differential equation yet. We have an equation with too many variables. The current is a variable. It's a function of time. The charge on the capacitor is also a function of time. So we have current and we have charge as time-dependent variables. So there's too many variables. Everything else is a constant, but this I and Q are variables that are things that vary with time. And so since we have two like varying quantities in this thing, it would be nice if these two things were related in another way besides this one equation. Well, it turns out they are. Current and charge are related in another way. Current's charge per time, or current is the rate of change of charge, say, that's building up on the capacitor. So what we're going to do is make this substitution. So we're going to put in for I, we're going to put dq dt. Now this is a differential equation. I misspoke earlier. Now it's a differential equation because it's a single equation that is relating Q and its derivatives. So this is a differential equation for the charge on the capacitor, right? So the strategy that's used to solve this thing is called separation of variables. You separate and integrate. So what we need to do is separate the Q's and the T's. Q as a variable and T as a variable. So there's a few different ways to do this, but I'll just kind of show you my own style. We're ultimately solving for Q as a function of time. Also, since we're solving for Q, what I like to do is just clear the coefficient on the thing that I'm trying to find. Okay, and what I mean is to get rid of this minus 1 over C that's kind of multiplying it. So what I'm going to do is multiply every term in this whole thing by minus C. And what that will do is get rid of this, this coefficient on the Q. So you can see if I multiply by minus C, that will kill the minus 1 over C on this term. I will get a minus C times this term. We'll change this term into this. And then if you multiply this by minus C, you'll get this. So each term has been simply multiplied by minus C. Right, so now we're here, right? Then what I'm going to do is just put this term with the derivative on the right. So all that's been happened is I just carried this guy over here by where the 0 is, just popped him over there. Okay, so now you're here, right? What we need to do to solve this thing again is to separate the variables, get the Q's on one side and dt on the other, right? So it's possible to go off on a bit of an algebra adventure with this. So this is something you're going to kind of want to run through a couple times to save yourself some trouble. But the key thing to remember when you get to this point is to take this entire left-hand side and put it under the dq, and then everything else put back on the left. So to see what I mean, I've just brought this q minus epsilon c under the dq, okay? And then everything else I'm going to herd back over to the left. So it's going to look like this, okay? Like the dt went over there, the rc I brought under there, and then the negative sign. Right, so again, just to, I'm going to replay it one more time because it's worthwhile. Bring the q minus ec, epsilon c, under the dq. Do that first. And then everything else, put it back on the left-hand side. Then we've successfully separated the variables. And you can kind of tell what's going to happen next because we have an expression with dq's and q's only, and then dt here. So then what you're going to want to do is then integrate both sides. And we're going to integrate on the left from where we start our stopwatch, 0 seconds, to some arbitrary time t. Okay, because the point is we want to know charge at any arbitrary time. On the right-hand side, we'll start with no charge on the capacitor, and then at time t, we're going to have some arbitrary charge q on the capacitor. And so now we're ready to integrate this thing. Left-hand integral is pretty easy. The dt just integrates to t, and then plugging in the limits, you'd have t minus 0. So it's just going to go here. Right-hand side, it's going to integrate to the expression would be log of q minus epsilon c. But now this is a possible pitfall. You do have to plug in the limits. So you'd have log q minus epsilon c, but then you'd have to have another minus log, and then you have to plug in the 0 limit. You'd have minus log of minus epsilon c. What I did here, and I did leave out one line of algebra, I would have log of q minus epsilon c, and then minus log of q log of minus epsilon c. So it's kind of like one of those situations where you have log a minus log b, and that's the same as log a minus b. So I did that here. All right, so once you're here, now all we got to do is solve for q, because if you remember, the goal was to solve for the charge as a function of time and the current as a function of time. So now what we're going to do is just solve for this for q. So once we're here, what we need to do is isolate this q. So the way to get at it, since there's a natural log here, is we need to exponentiate both sides, or as a lot of the students like to say, we're going to e it. So you e it on both sides, and you'll get e to the minus 1 over RCT on the left, because you e it on this side. And then if you e it on this side, you'll get rid of a natural log. And so you'll just have q minus epsilon c over minus epsilon c. Well, now all I have to do to solve for q is multiply the denominator over and then add epsilon c over. And so doing that, that's multiplying the minus epsilon c over. And then finally, what you get is this expression. And what this is actually this exact function, right? So this is an exponential approach to epsilon c. You can kind of tell that because if t were 0 here, then e to the minus 0 would be 1, and this whole term would go to 0. So at t equals 0, you do get a charge of 0. If you put in t equals infinity, you'd have e to the minus infinity for this last term, which would basically be 0. So you'd have 1 minus 0 gives you 1. Oh, so at t equals infinity, the charge builds up to epsilon c. So this is an exponential approach. This orange box expression gives you that graph over there on the left, okay? Well, once you have the charge as a function of time, now what's left is we need to get the current as a function of time, but that's easy because now all we got to do is take the derivative. Now, before we actually mathematically do this, you can see that when the current is the rate of change of the charge, you can see that's huge at the beginning, and that's why this is big at the beginning. And then the rate of change of this thing flattens out, and that's why the current then approaches 0. Right, so the bottom graph is nothing more than the slope of the top graph. So what we need to do is just take the derivative of this expression to get the current. So if we take the derivative of this first term doesn't even matter. That'll be a constant. And then when you take the derivative here, you're going to bring down a minus 1 over RC in the front of this thing, right? And so then you're going to get this expression then for the current. And you can see the cool thing about it is this orange boxed expression here does agree with our graph, which is an exponential decay from epsilon over r. And so that's how you derive this dependence of the current in the circuit with a resistor and a capacitor. So again, in the short going, this thing acts like a wire. Tons of current raging through at the beginning. The current dies down as the capacitor fills. That's how you get can think of the current dependence. For the charge starts off at 0 and then builds up and approaches a fully charged capacitor if you wait a while. So ultimately, if you can just kind of remember these two behaviors, that'll get you most of what you need on the Physics C exam. But to really clean it up, you want to know how to actually derive these two things, and that's by setting it up with a Kirchhoff loop. Um, all right.